Okay, here we are with part 2 of inductance basics. Just to finish up with this, because I kind of rushed this, the analog to Newton's second law then in mechanics is, in circuitry, is going to be EMF is equal to negative L di dt. And so L is analogous to mass. L, inductance, is really like, it's like an electrical sluggishness. It tries to resist changes in current. And the reason it does that is because it doesn't want the flux in it to change. And so let's get you there now as far as how that works out. Okay, so let's say that we have a solenoid here, and the solenoid has a radius r and a height h. The height is, I'm calling the height the distance from the first winding to the last winding. And let's say it's tightly wrapped. And here's a current, and I'm going to say the current's changing with time, but I'm not going to specify just how fast it's changing with time. But it is changing with time, and so what's happening is there's a change in flux in here. And so going to Faradays Law, Faradays Law tells us that the EMF that will be induced is negative N d phi dt, the derivative of flux with respect to time. So that's going to be equal to negative N. Now, the derivative of flux with respect to time for flux, I'm going to put, it's going to be just the B in here times the A. Now, I am assuming, by just calling the flux B times A, I'm assuming that the B is uniform in here. And it's pretty close to uniform in there. And I'm also calling that A, that's the cross-sectional area in here. So think of a cross-sectional area in here, that's A. Okay, now it turns out then that the B in here is going to be equal to it's equal in a solenoid, it's equal to mu naught times lowercase n times I, where that's the turns per length, and this is the current through there. So I'm going to just substitute in mu naught times n times I, and for A, I'm going to put in pi times r squared, that being the radius of the solenoid. Okay. Now this is telling me to take the derivative with respect to time, so I can pull out anything that's not changing with time. I can pull out all the constants, and so that's going to be the EMF induced is going to be negative N, and then it's going to be I'm going to pull out the mu naught, the lowercase n, the turns per length, the pi, and the r squared. And then so I'm just left with di dt. So here's the thing. Do you recognize E is equal to negative some constant times di dt? So you see what this is? This is L. This is the inductance. That's the electrical sluggishness. That's what that is. Let me pretty that up a little bit. So it looks like L is going to be equal to, L looks like it's going to be equal to N times mu naught. Now this N is really the turns per height of the solenoid times pi r squared. So L is equal to mu naught times N squared times pi r squared all over H. This equation right here tells you how to calculate the L if you're given the physical characteristics of the solenoid. It's kind of like capacitance for a parallel plate capacitor is equal to K epsilon naught A over D. This is only true for a parallel plate capacitor. And this one is only true for this type of a solenoid, where it has the core of it is actually air. Okay, so this is how you calculate the inductance of a solenoid, and you see how that's just going to turn into then if I put that in, it's going to be that E is equal to negative L, where L is all this stuff, di dt. Now, L has some units. L, inductance, has some units. And so let's talk about those units right now. The units for L, if I transfer that other equation there, the units for L are going to be called the Henrys, named after Joseph Henry. So L will be measured in Henrys. I don't mean to say L is equal to Henrys. It's measured in Henrys. Okay, but I want to make sense of what the Henry is. And so I'm going to bring the L on the other side, or the di dt on the other side. And so L is equal to negative E over di dt. So apparently, 1 Henry is equal to, I'll write out Henry. 1 Henry is equal to a volt, because E is in volts, 1 volt over, and now di dt would be 1 amp per second. So that's what a Henry is. It's 1 volt per amp per second. And I want to be a little more specific there. If I tell you that we have an inductance, an inductor that has an inductance of 3 Henrys, this means, so an inductor with an inductance of 3 Henrys. Hey, we can talk about the capacitance of a capacitor, or the resistance of a resistor, or the inductance of an inductor. And so an inductor with an inductance of 3 Henrys means that you will induce, or it will induce, a voltage of 3 volts. 3 volts for each 1 amp per second of current change. That's what that means. So more specifically, what I'm saying then is if you have an inductor, that's 3 Henrys. So 3 Henrys means that there'll be 3 volts for 1 amp per second of current change. Then if the current is not changing, you won't induce any volts. But what if I told you that you have this inductor and the current is changing at a rate of 0.5 amps per second? Well, if it's changing at a rate of 0.5 amps per second, since this is a 3 Henry inductor, that's what L is equal to, 3 Henrys, then we know that it will induce 3 volts for every 1 amp per second of current change, so it's going to induce 1.5 volts. So this will have, the EMF that's induced will be 1.5 volts. The direction of it depends on which way the current is moving and if it's decreasing or increasing. If the current is decreasing or increasing. Okay, those are the basics of inductance. We'll get into it a little bit more in the next video. All right, see ya. Thank you.